Okay, my friends, fabulous day today. Ghost particles could be behind the heaviest elements. A new model of quantum interactions. No, there's a new atomic model, which is called Dipole Electron Flood Theory. It does have new quantum interactions, yes, but it's a new model. It's not just quantum interactions that's new. The entire nucleus of the atom is new, which accounts for exactly what they're talking about here. And they're saying, and now big atoms demand big energy to construct. A new model of quantum interactions suggests some of the lightest particles, which I'm going to show you right now, in the universe might play a critical role in how at least some heavy elements form. They have no idea how the heavy elements can occur. I'm going to tell you how they occur right now. They occur because of enzymes, which are extremely elegant little chemistry sets produced by bacteria that create half-lives of all of these atoms, and they can upsize. They don't just decay downwards, they can decay upwards. I'm going to show you, it's quite obvious. You look at the list of isotopes. The isotopes can go down the periodic chart, or they can actually go up. And when you have enzymes doing chemistry at literally up to trillions of times a second, they can change all these things into back and forth until they make whatever they need to make. That's what an enzyme does. It's an extremely exotic little chemistry package. And this is what accounts for all of this, and it only can happen because of dipole electron flood theory. That's the only way that any of this could ever work. And they're coming around to realizing that now. Because I have the evidence. This is not just a theory. Here comes the evidence now. Okay, they're basically proving my theory for me. They're saying ghost particles, which are these neutrinos, could be instrumental in creating everything. And that's correct, because they do create everything. Everything is made out of these black and white particles. And let me just show you the particles first. These are the particles right here, this black and this white one. This is from Fermilab. They did this research and found these particles, the black one with a glowy edge and the glowy one here. Now, we found them in our light research. They found them as a decay from huge particles smashing in bits to pieces. We found them using the tiniest particles, which are light. So these are light. This is what light is made out of. And then we not only found these, we were able to separate them coming through this venturi. We accelerated the light, we were able to see the photons, we were able to see the neutrinos, all the things that they will discuss in a minute. I will speak about it. But this is what Fermilab and CERN and so forth do. They smash protons and neutrons together and get all kinds of debris. They are actually smashing these together, which as a neutron has, let's say, 1824, and a proton has 1823 of these particles. When they hit together, it's just a batch of debris. And X particles means they might have one this big. All right, the dark matter is always in the center of these. All right, so you never see it. You look at it, you say, there's no dark matter there. Whoops, there it is right there. It's inside the center. That's what dipole electron flood theory is. There's nothing but electrons that we ever see. They bounce back at us. All right, so this is not what it is. It starts here with photons. It actually starts with these little particles. They see them, they just don't know what they're seeing. And we do, because we started with light. So what we did was took a light and we accelerated it. This is just the beginning of acceleration. And it's pushing through all the other fields and glowing. That's what creates the wave, because they say wave particle. Yes, this is the wave because it has to push through all the other fields. The particle's right in here, and I will show you the particle right now. This is the particle coming forward. The wave is now being all stretched out, you see it? And it's pulling the particle right out of its own magnetic field like a jet fighter. And right here, it starts here it's starting to become neutrinos, and we can see them gaining energy, as I will show you in a second. And right here, it actually takes on a photon to become a photon. Photons usually only happen when they bounce back from what they're bouncing into. You see them as a full-fledged photon. Normally, and that's what you see as light. Normally, they're just passing through the air, and they're neutrinos. They have all different values depending upon what they're crushing through. When they get to where they're hitting each other really hard, because they're backing up. And it's going to back up as it gets closer and closer to whatever it's going to impact with. It's going to get more and more and more energy. It's going to be more and more visible. I'll show you that happening right now with this particle. All right, so don't forget, that's the neutrino faces, the flavors they call it. So here we go. No acceleration, well, a little bit. Full acceleration, impact. On the way, it is the neutrinos. That's a neutrino. That's a neutrino. That's a neutrino. These are neutrinos. That is a photon. Now, why is it different than the neutrinos if it's light? What's the difference? Why shouldn't this be exactly like this? It has something to do with the compression against whatever it's going to impact with. So as they go through the air, they're just sort of, they're going to bang into things here and there, because the air is full of particles too. There's no empty space. There is none. Not in space at all. There is no empty space anywhere. So they're going to sort of back up a little bit, but mostly they're going to move sort of freely. And they might, you don't even see them. All right, let me back up a little bit, because this can be confusing. Let's start with what we're actually looking at here. This is all light coming through here. All this is light. Light, 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 light. All you see is this ones. Why don't you see light up here? It's coming through here. Just exists exactly like this. Up here there's light. You don't see it. All right, Roger, why? Tell us why. Why don't we see the light, Roger? Tell us why there is no light there. Well, the reason is there's no concussion here. And you say, well, why is there concussion here? Well, the concussion here is because they are dead in line with the Venturi, which is here. So as their fields come forward, 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 they push back. So this feels like it's getting close to the target. So it starts to glow. As the neutrinos get closer and closer, they grow more and more and more energy. And here it looks like a little Oreo cookie. All right, now, you don't really see them down here, you don't see them up here, because they're not impacting with anything yet. Now, at this point, they're starting to be pushed back at, and well, let me just show you that so you understand the pushback effect, because it's starting to push back out to here now. All right, and here's what the pushback effect is right here. It's pushing back. That's why these are starting to glow. They're coming through here. It didn't just show up there from nowhere. And that didn't just show up there from nowhere, nowhere. They were there. They weren't illuminated enough because of the pushback. And that is what a neutrino is. It gets brighter and brighter and brighter and brighter, and then all of a sudden it's a photon. That's what a neutrino is, and that's how the flavors change. And this is because of this field right here. Look at this carefully. You see that field coming back? That's what's called reverse EMF, reverse electromagnetic field. All right, so what happened? When it exploded here, it exploded backwards, making this illuminate, 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 but even these illuminate because it's just it's an atomic, a subatomic nuclear explosion. This was, light is part of a nucleus. A very small part, all right, because that's a proton, let's say, in the standard model. Well, my model says that's a proton, all right, but every single one of the light particles is made of two of these, and these are dipoles. They're magnets, all right, they're magnetic, just like these. They're almost identical to this exactly right here, and as it moves through the air, The magnetism of it points it to the Earth. That's why they say there's upspin and downspin. All right, and as it spins, the only reason it spins is because it's interacting with these particles that are in front of it, hitting it, and the leading one charges up and flips to the back, and then the one that's uncharged comes to the front, and they just spin like that. And I can show that happening too. So don't forget, here it comes, energy, 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 photon, because it thinks it hit a wall. This is coming back. It's just like it hits against a wall right here. That's why you're seeing it as a bright light, which it would do if it hit a wall. So here it is right here. Here's the upgrade. CERN Large Hadron Collider will undergo a major upgrade to increase its instantaneous luminosity. That's where they can see the glow, allowing precision measurements of known processes and the search of new physics. The renewed machine requires an upgrade. Several sub-detectors of its experiments, including silicon trackers. Now listen to this. This work focuses on the design and integration of novel, which means new, radiation-hard, monolithic CMOS pixel sensors for new trackers. All right, this goes back to 2019 that they published this. Now, I think they shut down earlier than, well, no, I guess it was 2019 because they came back online 2022. It took 3 years. But this was for this CMOS technology. But the only way they could do it was to create these radiation-hard monolithic CMOS pixel sensors. So what does that mean, radiation-hard? Well, when these big chunks come out, if that hits the CMOS, it destroys it. Yes, I agree. No question whatsoever. Whoops. My dark matter fell right out. You see, dark matter right in the middle. It sits right in the middle. That's why we've never seen it. It's in the middle of everything. Everything's loaded with dark matter here. Light has dark matter and not dark matter. All right, so what happens with this CMOS? That hits a CMOS pixel sensor and it'll destroy it. It's just too much input. Like I said, the glass and the bowling ball, we know what happens there. So what they had to do was make, I'm sure, no, I'm not positive, but I would bet your life on it, that they put in one layer here and another layer and another layer and another layer and another layer until they got down to where all of the big chunks got absorbed and you ended up with the light little particles, which is the only ones you wanted to see in the first place. So they may be getting down to where they can see what they had hoped to see in the first place, but never could. But before you can do anything, you got to be able to see it, and now they can see it, so God bless them. All right, they didn't realize it, but this is a dipole electron, or what does that mean? An electron has a lot of energy and glows like crazy and burns and does all that stuff. It's heat, it's electricity, lightning, static. That's what that is. That's that side. This side is dark matter, and it's all the weight. The two of them together they call a Dirac neutrino, which means two. Di is two. Neutrino. Now they say there's other ones called Majorna neutrinos, which they're sort of halfway. These are the neutrinos that are not quite fully fledged into the Diracs. Let's look at what Fermilab has to say about this. All right, because I did work with Fermilab a little bit down Lincoln for a while there, and it didn't go particularly well. But I did claim this. These are the muon neutrinos, which is a black ball. And these are the electron neutrinos. They're stuck together in a Dirac. I just showed you a second ago. The two are black and the white. Well, the black goes off on its own, and the white goes into a shower mode, which is exactly what we have here. Now, if these were stuck together, and they are tight as hell, they are very, very tightly held together. It's called the strong nuclear force, because this is in the nucleus. These particles are down in the nuclear particle range because a proton is in the nucleus. Well, these are what protons are made out of. So these are nuclear particles. So this is a nuclear explosion. These two come apart, which they did. They're not supposed to be apart, and they come right back together here instantaneously, boom, just like that, because they don't want to be apart. They can't survive apart. This is what they have to be like here. Now, what is the stable states of light? Because there's nothing but light. Let me show you electron flood theory. All right, I have a paper on it that details it somewhat. You know, I mean, it details a lot because it's very simple. It's what changed from the standard model. And let me just show you something that's more visual. All right, this is Dipole Electron Flood Theory. All right, this was made for me by my friend Oscar Rosales. Fabulous job he did. Now, this is what the actual proton would look like. And they are, I agree with, they get stable at a certain quantities here. There's stability, yes. But there are a huge number of electrons, which are the same number of electrons as there is dark particles. And the dark particles don't care about being on top of each other. They'll go right on top of each other. The white ones, they don't want to be, they want to get away. That's why they spread out immediately as they go through the Venturi. They hate each other. The black ones, no problem. They'll stick right on top of each other. They have no push against each other at all. The white ones push each other right out of the way, and they desperately want to be attached to the black. So here's the two particles. That's all that exists in the universe. That's it. We are made of these two particles in different balls called protons and molecules and so forth, atoms. All right, so this details it a little bit. And what is the differences? These are the only two that exist. Neutrinos have these different colored flavors. They're not quite up to snuff yet because they didn't impact. But when you see the muons and electron neutrinos, that's when you know they're impacted. Now, gluons are just the black and the white attached together. Those are electrons. We always thought that's all that there was a glowing white one. No. This is where dark matter is. It's attached to the black. This is the smallest particle that exists that is stable, which is a photon. It's two of these back to back. This is a bar magnet. That's a bar magnet. It's just like taking two bar magnets back to back. Simple as that. If you go above that, they're not stable anymore. They're not really in a stable state until you hit, for some reason, I can't explain it, 1824 neutral. 1823 is a charged particle, but it's right up in the zone of stability. So this right here is two of these. Each one of those has a dark and a white. They're polar. These are little polar magnets. That's all they are. All right, and they're side by side, and they come through the air, and they charge up, and they flip, and they charge, and they flip, and they charge, and they flip. Because this one, banging into everything in front of it, charges up, flips, charges up, flips. Just as I showed you right there. That one's going to charge up, and it's going to flip. This one's going to come in the front. I call it the muon wobble. All right, so let's just go right to Fermilab. All right, listen to this now. Pay close attention, because this is what I'm saying. This is really what a proton is. It says neutrons, which is this. Neutrons, protons, same thing. A neutron only has one more than a proton. A proton has a charge, because it's not equal. It's 1823. It wants to be 1824 to become neutral. Now, hold on. All right. I'm going to tell you right now, enzymes break apart molecules instantaneously, billions and billions of times faster than would happen in life, as they're going to say right here. So this is my proton or neutron. They're just exactly the same, except the neutron is an equal number, the proton is an odd number, which means it's charged. Even numbers are neutral. They have equal numbers. Now, neutrons, which is this, a neutron, transform into protons, which is one less, when they give up an electron. When they decay, emitting an electron. So they give up one of these, and an electron and a neutrino. Well, the electron is the electron and the muon, neutrino together. It's the same thing. So they know they decay like this. Now listen to what they say. This is very important because we're talking about nucleophilic invasion and substitution, which is nucleosynthesis, which means to change the nucleus, to rearrange the nucleus by invasion of these particles, all right, or breaking them apart. So you can break them all into little bits and pieces. They show this, they know this now. And they know that the proton is not one big positive. They're showing it now. They're finally showing that neutrons transform into a proton when they decay. They're still showing the protons and electrons in the neutrons, in a neutron or in a proton. This is brand new, and they're not talking about it. This is just, they're just showing it, saying, oh, well, now we know this. Well, they didn't know that before. All right, now listen to this. Ordinarily, this process of emission happens painfully slow, trickling away over the scale of decades or even centuries as the nuclei within large stars jostle, gaining, losing neutrons, frequently with few ever making the switch into protonhood at the critical moment. So and what they're saying is we have no idea how this happens, but we do now know, which is new as far as I'm concerned. Well, you're going to see the standard model says that's a big proton. And it's got made of like little quarks and things like that. Well, no, it's made out of dipoles, which is Dipole Electron Flood Theory. Now, let's go into Fermi. All right, so this goes way back, which I go way back on this too. Way, way back. My original theory was light is atomic vapor, which it is. And that right there, my friends, is the smallest particle that exists, which is stable, which is an electron, which is a Dirac neutrino. And this is Fermilab. So they're saying the neutrino, one of the most mysterious particles in the standard model. It's still mysterious. They still have no clue about it. Now, this is back in 2012. That's over 10 years ago. So this is the Dirac neutrino, and you know he was on to a little bit here and there. Don Lincoln, and like I say, I interacted with him, you know, substantially, and he just couldn't come to the understanding that our CMOS was the ability for us to see these particles, so it really didn't go anywhere. Now, he's saying if neutrinos have mass, and he says we know they do, they observe neutrino oscillation, which is that flip in there. One can ask whether a neutrino and anti-neutrino are one and the same particle. Yes, they are. That's the black and the white, the neutrino and anti-neutrino. All right? If the two are different, and they can be separated, they are called Dirac particles. Well, if the same, they are called Majorna particles, which is just that they haven't built up their neutrino-ness yet to become a photon. If neutrinos are Majorna particles, this opens up all sorts of new kind of physics. Yes, a kind of radioactive decay called neutrinoless double decay. Well, I don't know about any of that stuff, but let's just leave it here for the neutrinos. This is exactly what I have been showing you. These are the particles, and it does open up brand new physics. Now, here's the Fermilab again. Modern physics deals with some ridiculously non-intuitive stuff. Empty space isn't empty. It's not empty. light is everywhere. If you look out into the space, and it's just everywhere. And I can show you that light isn't empty because of all of the fields that are out there, as well as particles. There's fields everywhere. Everything creates fields. Now he's saying that the foam on the head of a root beer is complicated environment. Bubbles appearing and disappearing, dizzying display of change. Empty space experiences similar activity. Empty space experiences similar activity. Subatomic particles. That means smaller than atoms. These kind of particles out there. Winking in and out of existence, banging into each other. Glowing, stopping, glowing, glowing, banging, hitting, slowing down as they go forward. All right, it experiences similar activity. Subatomic particles winking in and out of existence. When they wink, it's because they got banged. These particles, subatomic particles, are real and have a measurable impact on our universe. Yes, they do. And they are fields out there that are just everywhere, saturated. Light coming to us is not coming at one set speed. As I have shown you already, light changes speed. It goes faster, it goes slower. The particles are the same, they just spin faster. See, this is the latest thing. They think there might be gravity waves out there, which there absolutely is. That's an artist's rendition. Well, here's the real thing. And this was taken by Dylan Carpenter with a cell phone. I'm not sure how he had it set up, and I can't get through to Dylan, so I can't do much about this. But he took a picture of the moon, and I understand why it's blue here and shifted red here a little bit. And all of these fields are in space. You see, every one of these spheres, which I'm sure are stars, I'm almost positive. Some of them are either moons or other planets or something out there. And some of them are who the hell knows what. But it is saturated out there. Light is not going to go through there at the same speed. Absolutely not. No way in the world. All right, there's blue coming in really hot and then just slowing down. So we know we can slow light down. No question whatsoever. You can't even tell there's two dipoles here until you get way out here. They started separating. You can see them. So that's something that quite obvious. This, you can see that they're attached together. Now, the reason you're seeing these here is that because that's the pulsation back against the particle coming forward. And you're seeing them show up. And that's why at this range here, you're starting to see dipoles all over the place. All right, because it's being banged back at. Same here, same here. But here, you don't get it yet because there's not enough reverse compression to make them puff up. It's called the Casimir effect. Two fields coming together, you get energy. And it's just an obvious thing. Now, I showed you that how fast the green is compared to the red. And it actually makes the red tumble like this. Normally they don't tumble, they spin according to the polarity towards the Earth. Now out in space, I guess they can just go any which way they want. But on Earth, they spin according to the polarity of where they are on the Earth. That's why you have upspin and downspin. And they're all like that. Everyone I've seen. Now, the only two particles that exist is this one here, the white one and the black one. That's it. That's the only two that exist. All the rest is just accumulations and changes of these two particles. The Higgs boson is when these two particles are together. These two particles separate, they become the neutrinos, muon and an electron neutrino on their own. When they're together and two of them are back to back, it creates a gluon. Now the Higgs, I'll show you the Higgs right now. All the rest is just, you see bottom and top and up and down, and this is about spins and neutrino values. It's stacking up, but it's the spin, up and down spin. Is the energetic particle up or is it down? That type of thing. It's, they just don't understand what they're seeing. Even like this, look, think about this. You see this? That particle is going this way. Why wouldn't this box be twisted that way? because it's spinning. But it's polarized towards the Earth. They all have that same polarity. The same with the red, the same with the green, same with the blue. But you can't really see the blue. Blue is just too much, too intense. What haven't I shown you? Well, these are Higgs fields. Now, you see the white particle? That's separated from the black, completely separated. But here they come back together and they make exactly like they were when they were light. From light back to light again. Remember these fields? This is as the light is coming through the Venturi and turning back into normal particles again. Well, as it came through the Venturi, it did the same thing. You see those fields? They're the same thing, fields. As it came through the Venturi, they were these same fields. When it came out of the Venturi, came back to these same fields. You understand? Here the black and white was together. The black can't get through, so the white went by itself, because they can squishy and get big. The black, only one size fits all, never going to change. So the white squirts through, but the black says, come on back. Instantaneously they come back together. But you see these white little spritzes staying up, they don't like each other. The white ones want to stay apart because they have fields. The field says, and they set up these lines. They call them interference patterns. They're not interference patterns, they're repulsion patterns. But the black couldn't care less. The black will be right on top of each other. That's why I say the black goes right to the center. It goes right to the center, and it becomes the core of every atom. And normally all we ever see is atoms. You only see the inside of atoms when you smash them to bits, or when you do like we did here and you can see light. Because light is nothing more than the particles that make up atoms. But when you look at this, you say there's no dark matter here, there's no dark matter. Well, yes there is. It's inside, because all that white wants to be attracted to it. And the black couldn't care less about being on top of itself, so it balls up in the center. Just like this. Just like this. That's it right there. And all those electrons want to be attached to that black desperately. So the ones that are really tight on there are blue. And they are tight. When they go flying off and take off, they never come back because they're so tight. They emit. The reds, they don't always go. The green usually goes, but the red is sort of is a loose particle, and it sort of drifts around. And they see this at Fermilab too. But this is the new dipole electron flood theory. This accounts for being able to make Mercury into gold, to be able to make all of these upper end heavy metals. They've never been able to figure out how anything could be bigger than iron. All of this stuff up here, where did it come from? They say, oh, it must have been from the Big Bang. Now they say, no, that's probably not true. And they say, well, it must have been from this. It must have been from something else. It must have been this or that. They have, at this moment, have no idea. And they never will until they understand this. And then they have to understand enzymes. And what do enzymes do? They work with the isotopes. They make and break molecules instantly. And if your body needs something way up here, it needs some gold, or it needs some iridium, or whatever it needs. And it's going to need all these particles. That's what life is all about. Even uranium, it's going to bump up these particles using nucleosynthesis. I call it nucleophilic invasion, which is the biological term, where biology does that. But it still does it, but it's made by enzymes. Enzymes make and break molecules instantaneously, and they can make them go up or they make them go down. Decay doesn't always mean going down. You can go up too, and they are so sophisticated, these enzymes, that in my world, they are like little stepping stones. They go, okay, we got it. You want some of that? We got it. You need some of that lead? We got it. You need some of this? We got it. And they just keep bump, 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 until they get up to whatever molecule you need. Let me show you what isotopes are all about. Once you understand isotopes and half-lives and enzymes, that's where these metals are coming from, because we're required to have them for life. But you need the enzymes to create the metals. So when they say, oh, the guy he's low on this or he's low on that, he doesn't have enough iron or this or that, well, you need an enzyme to create that chemistry. And enzymes come from bacteria. So this is a little bit of a step on chemistry, biology, the whole thing. All right, don't blow out on me. This is simple. An isotope is nothing more than the actual atom, but it either doesn't have enough particles or it has too many particles. That's what isotopes are. So what does it mean if it doesn't have enough? It wants to take some in. What does it mean if it has too many? It wants to give some out. Well, what happens in the bump reaction that I'm talking about, which is a nucleo bump? Okay, I'm going to call it the nucleo bump. It bumps it up. And how does it do that? Well, let's take, as I talked about, gold being made from mercury. Well, where are they on the periodic table? Gold is right there, Au. Mercury is right here, Hg. Mercury is cheap, but gold is expensive. Why? Can we convert mercury down to gold? Yes, absolutely. Can we convert mercury up to thallium? Absolutely. And how do we do it? We use isotopes. And what does the enzymes work with primarily? Isotopes. Let's take a look at what an isotope does to mercury. And first of all, mercury is a huge molecule, but it's a fluid. And it's Hg. Now, these are all the different sizes of mercury. It's not just one mercury. All of these are different mercury, they call them, but they have different sizes, which means they have more or less of these particles. That's all it is. That's all it is. So way down here, we need more. Way down here it says, boy, if you could give me some more, I'd be good to go. All right, now, you see this? This is a daughter isotope. Well, what does that mean? There's a half-life, which means in this particular state, it doesn't want to be there. It's going to decay. And how does it decay? How long does it decay? That's the half-life, how long it takes to decay. And what does it decay to? Well, Pt, all right, which is platinum. All right, Pt is platinum. So it can actually decay into platinum. It can go right past gold into platinum, but it can also decay into gold. You see here? Here's a daughter isotope is gold from this particular conglomeration. Some more gold. That's the daughter isotope. It's giving off gold. Gold, 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 gold. These are all what it can decay to. Now you got a bunch of gold, 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 gold. Now, can we go up from gold? I mean, from mercury up to thallium? Let's see. These are all isotopes. This is what I mean. The enzymes work with all of these little bits and pieces, but for them, a decay, a half-life is no problem. They do it thousands, tens of thousands, hundreds, even millions of times per second. So they can go and bring this all the way up to wherever they want to go, and they want to go up past thallium. We're still in mercury. We started from mercury, but now we're going up in thallium, and then we go to who the hell knows where after that. They don't even know what the isotopes are. All right, but we can do this. Look, it's just all gold, 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 gold. If we started with this much of an isotope, of a mercury molecule, and somehow we did the electron exchange, electron capture, we could make it go up to gold. Or I mean down to gold. But they don't understand what the molecules of the particles that make up the protons and the neutrons and all of the different particles. Because Mercury up at this size is not just a bunch of particles. It's literally at this place probably hundreds of thousands. All right, according to electron flood theory, 80 protons and 90 neutrons actually equates to 310,250 dipoles. All right, because there's 123 in these, 124 in these. So you multiply it all out, you got 310,250. So that's what we're working with here. And enzymes can do this so elegantly, it's amazing. Now this is the smallest mercury that exists. These are all mercuries. And you see they go from 90, 91, 92, 3, 4, 5, 6, 7. They're just adding more and more neutrons. But every time they add a neutron, it's 1,824 more particles. So they're going up with a gazillion particles here, way, way, way up. Now, I'm going to tell you at the end, where they end off up here, is 136. 216. So 80 plus 136 is 216. Hold on. All right, way up here, we're up in 394,000. So it's like 80,000 different particles in between, just in Mercury itself. And when these enzymes get in there and they start going, it's so unbelievable the amount of chemistry they can do, and they will bring it way up to where you need it. They can go up, and then from the Ti they can go up to the next one, or from the thallium they can go up to the next one. All right, this is the Fermilab again, the standard model, the most successful theory ever. Well, actually, no. All of that stuff is not particles. They are accumulation of particles. The W and Z bosons are the only things that exist. Now, this is, again, Fermilab. These are the particles that we found, the exact same particles. And they react exactly the way he says they react. All right, and you're talking about all kinds of different particles. Now, this is what's called a fixed particle. It does not change size. It's one size fits all. That one is the glowy particle. Forget this. This is just wrong. This is not correct. These are the only two ones that exist. They can see bigger ones and smaller ones just because they're seeing them from further distance away, I believe. But these can get big and small, yes. These don't. These are same size. And he even says it here. I don't know why they did this. Listen to what it says. If you magnify an extended particle, that's this one, extended. If you magnify it, it will look bigger, but you have to magnify it. A point-like particle will not change in size, but the more closely you look at it, the stronger the field surrounding it becomes. So this won't change in size, but the field gets bigger because he says there's no size to them. There is nothing there. And I can sort of agree with that. But the closer you look at it, what does that mean? If I get right down there and look at it close, it gets bigger? No. You look at it and add more energy into it, it fights back and it gets bigger, yes. And that's what they were doing. That's why they couldn't use the CMOS. And he wouldn't listen to me about the CMOS. I said, we can see them, Don. And, oh, no, actually, well, anyway, I don't want to get... Anyway, in summary, extended particles have a fixed size. The black ones never change, I agree. And they have a fuzzy edge, I agree. Point-like particles are mathematical abstractions, no size whatsoever, but the particles have an extended effect. And that's the field that he talks about. Looking at it closer, it gets bigger. That is like the way I'm seeing it, it's almost like a soap bubble. How they, if you add something that penetrates into that bubble, I don't know, but they get bigger and bigger and bigger, and they can get very, very powerful electricity. That's the glowy part, can get extremely powerful right there. That's some serious power. And all that is from a cheap little red laser. And I don't see why we shouldn't be able to get some free energy if we did something like this. All this is shooting it into a Venturi, and over here, if you could put a harvester, something like this. The laser shoots it through. The black can't get through. It just can't get through. So the white is the only thing you want anyway, which has no weight and it has no mass, and it just has energy. And you filter that down through a photodiode into some kind of a absorber device, either battery stack or whatever. Just run it right out to whatever you need. You take a little bit back and you put it back in your laser, shoot it out. At minimum, if this is true, we should be able to use 5 watts and get back 1,000. That's 200 times more energy than we used to start with, and we did not add any energy here at all. And all we started with was cheap little laser lights. If this would work, that would be pretty cool. And it doesn't require anything. You could carry something like this around, just like this. Just like that. Carry it around, plug anything you want, out in the woods, out in a disaster area, fires, you just click it to hit this kind of AC, DC, 200, whatever you want. 110, 220, USB, wouldn't matter. And again, no grid, no nothing. If it would work, but I haven't seen anybody take any interest in it. And I'm not doing it. I'm just too old to get too deep into this anymore. Now, this is Fermilab showing their Higgs fields. When they smash, and they can see the Higgs fields, yes, but it's just in a bunch of debris. When we see ours, we see a magnificence. Magnificence. And you see right there, you see that one? And it banging right into the edge of this disk, and I believe it's creating this field. And I believe they all create fields as they bang in to other particles, which would be the black ones, and they just start spinning. Because they started this way on the other side, as I showed you. I think I pointed this out before. They started coming in this way with the same fields, same exact fields. No difference. When they come back together out here, they're the same fields. Again, they return to the same, from whence they came. Okay, I believe that the way that these metals are formed is from enzymes bumping the particles up. All right, because they can decay up instead of down, as I showed you with isotopes. And enzymes work so fast they could easily do this and create any particle you want. Because we have uranium in us. There's uranium in our blood. Where'd that come from? They say, oh, it came out of the environment. Well, where'd the environment come from? Basically, everything we're walking on was alive at one time. So life, with its enzymes, brings whatever molecules it needs all the way up to metals. And then when things die, and the blood and so forth of gigantic creatures accumulates, specific gravity actually brings those metals together, and you find them in geography, geology. They collect according to specific gravities in layers, just as the Triassic did, with the red bed, gray clay, and black cap. All right, that's specific gravity. That's where things float down in the solution, and different weights settle in different layers. And it's all over. You use a centrifuge, and you see it, layer, all these different things according to how heavy they are. So I think a dipole electron flood theory with enzymes and half-lives and isotopes accounts for the metals that nobody can seem to account for. And yes, these things do throw off tiny little particles, and they gain them as well, depending upon what the enzyme wants to do with that particle. Whatever biological requirement there is, that enzyme will know what to do. I mean, the bacteria will know what to do. to send out a package to synthesize this nucleus up to the next one, up to the next one, up to the next one, up to the next. It's a bump up. It keeps bump, 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 and then it gets to wherever it has to be. If it's uranium, it's uranium. All right, let me try to wrap this up in a little bit of a package. We saw the light. We saw the particles, the neutrinos. My claim is that those neutrinos are these little bits that are the particles that make up protons and neutrons. Now, I also claim that enzymes, which are from bacteria, can break these things apart instantaneously, and like they break down your food. Your food is nothing more than big chunks of particles like this, meat and carbohydrates and fats and all kinds of different things, starches, and they have to be broken down into little bits and pieces, and that's what enzymes do. So enzymes can do instantaneous chemistry that's just unbelievable, and this is what an enzyme looks like. That's how complicated they are. Every one of these little colored spots here, the red and the blue, is a magnetic moment. And it's because this, when it gets to where it's going, it comes out in a ball called a ribosome. When it gets where it's going, it does that. It just pops out of a sheath, and it creates an exact identical to this every time. And that's what does the chemistry in your body, is the enzyme. Now, here's how they're produced. Bacteria create them. They're called ribosomes. And every bacteria creates a different type. I mean, there's zillions of different bacteria, zillions. Now, those ribosomes come out, those little balls. And where they get to know wherever they need it, they unsheath. And something on them tickles them to say, I'm up against something that has the chemistry, open up. And it opens up and it dumps an enzyme onto it and kills it or breaks it down for food or kills an invader or whatever. It also can happen and create proteins, which are building blocks. So enzymes and proteins are basically the same thing. This one builds stuff, this one kills stuff. It's a build and a kill. Now, what about metals? We started this talking about metals. Where all these metals come from? These are transition metals. You see this? Titanium, vanadium, chromium, magnesium, iron, cobalt, nickel, copper. All of those are in your blood. And way up all the way to uranium. I'll show you what's in your blood in a second. Almost all iron is just everywhere in your blood because that's what carries the oxygen. These are carriers. These carry things because of these charges. And here's what it says. Transition metals form colored compounds and complexes. The colors can vary depending on the charge, 3+, 2+, 5+, on the metal ion. So these are metals. And the number and type of groups of atoms called ligands. These are attachments to the core. These are the little attachments. They call them ligands. Because this is a carrier. This goes in your blood and carries all these things through until somebody else comes by and says, ooh, I could use one of these. It's okay, give me 2 of those and I'll give you 1 of these, and it's all done. Now, this is in aqueous solutions. This is in the water in your blood. The ions form complexes with the colors shown to the right. And here's the colors. And I find these all the time in my fossils. They're just everywhere. You see this? I said that there's a program that creates these metals. These are the program codes, the amino acids. There's 20 of them. And they create the program inside these ribosomes, which is they come out in these polypeptide chains, and they have to be exactly these different sequences, and that creates a program inside of the ribosome ball. Then the ribosome ball has that program ready to go to attack something, to break something down, to do whatever it needs to do. And they reside all over your body. They're everywhere. They're flowing through, and well, I think a new article just came out today about it. The fluid-filled highway. I've been talking about this over and over and over for many years now, and now they're finally realizing this is where all of your biology in your immune system is done, and it's done using enzymes. Without the enzymes, you can't attack things. Right, you see this? That's a program. It's just a program. And it's got a little sheath around it. It's got some chemistry on the surface of it that says, look for these sequences of molecules. If you see them, touch them, pop yourself open and kill it, or break it, or do whatever you want to do. And that's that ball coming out, which is right there. The sheath pops off, and it does its job. All right, so don't forget now, they have literally no idea where these metals come from. But we work with transition metals in our bloodstream. These are all the metals, well, here they are right here. This is their atomic weight. And these are up above iron, which iron is here. Now you go to cobalt, nickel, copper, zinc. All right, so cobalt, nickel, copper, zinc, arsenic, selenium, all the way up the line. Look at all of these are in our blood. Thallium, way up here. Thallium is above mercury. Lead is in our, uranium is in our blood. In small quantities, but apparently we can bump up. Otherwise, there's no other explanation for this, none. And nobody can come up with an explanation. However, enzymes do so much chemistry so fast, and they bump things up. As I showed you with isotopes, we can go down to a lower, or we can go up. They go both ways. Let's take phosphorus. Let's just look at phosphorus, because I look at that a lot, because that's what membranes are made of. Look at this now. Don't forget, phosphorus is here. Sulfur is up. Silicon and aluminum are down. So phosphorus can decay to a daughter isotope of silicon or aluminum down on the low end, magnesium, silicon. And then we're up to sulfur. As soon as it hits stability, the next thing goes to sulfur. All the way up, sulfur, 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 sulfur. So obviously some of them have a propensity to jump and bump up quicker than other ones, I'm sure. But you can see this jumped up from phosphorus up to sulfur. So there's no reason we can't bump all the way up to uranium or whatever your body needs. These enzymes will provide. That's my take on it, and dipole electron flood theory gives that ability to happen because there's so many of these dipoles.